All right, so it's time to go ahead and begin today. So today, the main topic is what a multiplexer is. And the multiplexer is going to be part of lab 3. And just like previous labs, after today, you'll be able to start lab 3, but you won't feel the tension until we talk about the filters on Tuesday. Okay. So there's just a few terms that I just want to go over before we start talking about multiplexers, just because these terms come up a lot, especially when you take the follow-on class, the CP233. So first of all, there's this term byte with Y instead of I. Does anyone know in the digital world what's meant by the word byte? Exactly. Yeah, byte means okay, then there's this other term, word. But word has a particular meaning. This one's a little tougher. Say it again, please. Well, actually, a word can actually be that or just about anything. Because what the word refers to, like a control system, like a microprocessor, is how many bits for a particular piece of data. I mean, that data could be hex characters, it could be a binary number, it could be an instruction to a microprocessor. I mean, it's virtually anything. And most often, the number of bits in a word depends on the microprocessor you have. For example, you've probably heard, 32-bit microprocessor, 4-bit microprocessor, 16-bit. Back when I was an undergrad, we only had 8-bit microprocessors. And, the number of bit microprocessor refers to the number of bits that most of the registers inside the microprocessor can store and hold. Now, we're going to learn what a register is. But right now, the reason I bring this up is just so you know, the term word, the number of bits it primarily depends on the microprocessor. Okay, and this is my shorthand for microprocessor. So in CPE 233, and I put the structural model, okay, the structural diagram of the microprocessor that you're going to be building in 233 is on each of the tables. And please leave this on the table because I need this for all my techniques today. And I'm just showing you this as a reference, okay, to try to tie in, some of the things we talked about in this class, in that class. So, don't get overwhelmed or think, oh my God, no, that's what 233 is. But this microprocessor that you build in CP233, it's a 32-bit microprocessor. If you look at the diagram, you'll see a lot of flashes with 32. Remember how last class we talked about that if you have multiple bits on a input or output, right, you put a slash with the number. Well, that's what it means. Right? Everywhere you see a slash 32, there's 32 bits on that line. So the word for the microprocessor in CPE 233 is 32 bits. So when you take that class, you'll be dealing with words that are 32 bits. Okay, but again, it depends. Like if you have a microprocessor that's 16 bits, well, words would be 16 bits. Back in the old days, like I said, when I took this class, we had 8-bit microprocessors, so words were 8 bits. Okay. So what do you think a half word is equal to? That's an easy, right? So yeah, it's just half a word. Whatever the number of bits for the word.
What about a nibble?
I was going to ask that. Does anyone know what a nibble is? Well, obviously you must know because you know the term, but does anyone else know what a nibble? You don't hear this one much anymore. That's really like old school.
Like, half a byte.
Well, good guess, right? Because you would think it's less than a byte, right? Because a nibble's like a small byte. Yeah, a nibble is 4 bytes. Or 4 bits, I'm sorry, 4 bits. Yeah, so it's like half a byte. Yeah, you don't hear it much anymore because again, most systems, microprocessors have much more bits than 8, so you don't hear that much anymore. Okay, so again, just a couple of terms that's good to know, not only for this class, but any digital class you take. But now the rest of the class, we're going to concentrate on what a multiplexer is. And you can see we've got quite a bit up here. I want to give you some basics about the multiplexer. Then I want to show you an example of a logic gate circuit that makes up the multiplexer. Then we're going to look at a timing diagram for a multiplexer. Then we're going to talk about how you would model a multiplexer in System Verilog by first doing a comparator example. So I'll talk a little bit about what a comparator is. Now, a comparator is not in lab 2 or lab 3, and I don't think it's any of the other labs that we do this for. However, a comparator could be something that you would want to use for your final project. And the reason I talk about it at this time is the example that I do modeling a comparator. If you understand that, then to model a multiplexer with System Verilog should actually be easy. Okay, but anyway, that's sort of the game plan today. Also, you can see I have the truth table for an AND gate up there. That's going to help us with this logic gate circuit when we get to that. But first, some basics on multiplexers. So this is the symbol for a multiplexer. Okay, it has this unique symbol. A multiplexer always has one output. Okay, so always one output. So here, our output I labeled F, and on the multiplexer itself, I just put out. You can label the output whatever you want. The multiplexer always has multiple inputs. So that's why, I did this with the dashes, right? Because, there could be 2 inputs, 3 inputs, 4 inputs, 5 inputs, in theory, out to an infinite number of inputs. Okay. Now, even though you can have any number of inputs, most often the number of inputs you have on the multiplexer is equal to some whole number power of 2. So usually you'll have like either 2, 4, 8, 16, 32, but there are cases where, like I said, you can have something other than a whole number power of 2. Okay. Now, the number of bits that you can have on each input as well as the output can be any number. Sometimes your number of bits is just 1, okay? But you can have 2 all the way up to, again, in theory, up to infinity. Okay, so it can be, any number of bits on each input. So the way I drew this, because I didn't put a slash, this would represent a single bit input, right? All single bit inputs. But, let's say each input had 4 bits. Well, then you would see the slash. I'm not going to put it through the line just because I don't want to break. But I don't want to confuse. So slash. That would represent each input having 4 bits. And if your inputs have 4 bits, the output would also have 4 bits. Okay, the number of bits the output has is the same as the number of bits an input has. Okay. Now, these are referred to as the data inputs. That's why you see D. They're not always labeled D, but it's understood that, this is some sort of data. Again, the data could represent anything. Those 4 bits could represent a binary number, it could represent color, sound, whatever it may be. Okay, whatever the designer decides it to be. But then you have this other input, SEL, and SEL is short for select. And you may recall on the activity on Tuesday, right, when you're doing the structural model, remember there was that one block that had an SEL input. Well, that was representing a mux. Okay, so this SEL, it's also a input, and the number of bits that you have on your select input depends on the number of data inputs, okay? So if we have two data inputs, I would only need one select bit. Okay, now I'll explain why that's so coming up. Okay. If we had 4 data inputs, we would need 2 select bits. Okay, if it was 8, we would need 3. Okay, 16, we would need 4, and so on. Okay, and you see the reason why there's this relationship that you see here between the number of data inputs we have and the select bits is because a mux basically acts like a multi-position switch. You know, probably the most popular or the most familiar multi-position switch that you've run across is, you know, a manual hand dial. Right, a hand dial you manually turn, right, to select from multiple things, right? You select one of those multiple things. Well, the mux chooses between multiple data inputs with the select bits. See, the select bits are going to determine what data at the input gets connected to the output. Okay, so you see the mux is kind of like a selector, you know, and that's why this input is called the select, because it selects which data input gets connected to the output. Okay, so let's say I had 4 inputs. I'll draw another mux symbol over. I have 4 inputs, and you know, this input I labeled 0, this one 1, this one 2, this one 3. This has data D0, this has data D1, this has data D2, this has data D3. And let's say they're 8-bit data. The output would also be 8-bit. And then I have my select. Okay, well, since I have 4 inputs, and this select input chooses which of those 4 gets connected to the output, how many bits is the select input going to have to be in order to choose between 4 things? 2, right? Because that goes back to the 2 to the number of bits gives you the number of values, right? So if there's 4 possibilities, I would need 2 bits. You see, your select line would be 2 bits. And if our select line is a 0, 0, right, a binary 0, that's going to connect the data on the 0 input to the output. So by putting a 0, 0 here, I'm now getting D0 at the output. If I put a binary 1 on the select, well, the data on input 1 is now at the output, right? If I put a binary 2 at the select input, the data D2 would be at the output. If I put a binary 3 for the select, the data D3 would be at the output. So you see, these select bits are determining which of the data gets to the output. Right? So you see how it's like a multi-position switch? It's like the select is your hand, if you will. You know, and it's choosing which one of these possibilities, these input possibilities, gets through to the output. Okay, that's how a mux works. And you see, the number of select bits does not depend on the number of bits the data has. Like if I change this, where now instead of 8-bit data, you know, say this was 32-bit data, like in CPE 233. Okay, this was all 32-bit data. Well, I would still need 2 select bits, right? Because the number of select bits is determined by how many inputs you have. It doesn't have anything to do with how many bits each input has. Does that make sense? Okay. All right, so if I had 8 inputs, I would need how many select bits? 3. All right, good. 16, I need 4, right, and so on. All right, so any questions up to this? This is the key thing. it makes sense to you that the mux acts like a multi-position switch, right? That's the key thing. If you understand that, you understand muxes. Okay, so now, again, just to kind of tie this into, you know, a future class, namely CP 233, look at that diagram for the microprocessor that you're going to build in CP 233 and tell me how many muxes there are. How many of these symbols do you see? 5. Or 4 or 5. Oh, 4, I can see. I can understand why someone might say 5, because there's that ALU that I know it's the same, but it's not quite.
Oh, okay.
But yeah, there's 4 there. There's a 4 input.
Oh, yeah.
Yeah, see the 4 input at the input of one of the ALU. And then there's a 2 input, and 4 input, and then there's one with 6 input. So looking at that, do you see the one that has 6 inputs, the one on the left? So 6 inputs, how many bits would the select line have to be?
3.
Yeah, it would have to be 3. I mean, you know, because if you only had 2, you'd only be able to select 4 of the 6, right? Yeah, you'd have to have 3, even though, you know, it doesn't have 8, you know, it has 6, but it would still need 3 to choose from 6. Okay. But yeah, the answer here is 4. All right, so any questions up to this point? Because the next thing we're going to do is we're going to look at the actual gate logic. Okay, an example. Okay, so here's the logic gate circuit. CKT, by the way, that's my abbreviation for circuit. Yeah, I don't think that's anyone else's. So that just means circuit by that. Okay, so this is a 4-to-1. What the 4-to-1 refers to is that there's 4 data inputs and 1 output. And like I said, muxes always have 1 output. Okay, so you either have like a 4-to-1, an 8-to-1, a 16-to-1, 6-to-1, whatever it may be. Okay. So you can see here, I labeled the inputs the same as what I did with the symbol, and I labeled the output the same. Now, here's a little review question. What kind of logic circuit is this? Is this SOP, POS, NAND, NOR?
So product.
Right, SOP, right? Some of the products, because we have the AND gates first, all getting bored. That was just a little review question there. Okay. And we've got these NOT gates now. You know, these are our data inputs, right? And here's our select bits. So S0 and S1, those are select bits. Okay, so we're going to fill out this truth table. You know, I don't think we'll do all 4 possibilities. I think once we do 1 or 2, you'll get the idea. But this will reinforce what we just talked about, that these select bits determine which data gets connected to the output. Okay. Now, before we actually analyze this circuit, let's look at the truth table for the AND gate. Another review question. Is an AND gate a universal gate?
No.
Oh, very good. Which gates are the only universal gates? There's 2 of them. Which 2? NOR and NAND. And remember, when we were talking about universal gates, and you know, we talked about, well, first of all, before I go any further, what do we mean by universal gate? I mean, a NAND is a universal gate, a NOR is a universal gate, but what does the term universal gate mean? Exactly, that you can, you know, get a NOT gate, you can get an AND gate, you can get an OR gate, and a NOR gate from a NAND, and same with the NOR, right? So we talked about that. And remember, when we were talking about those universal gates, we looked at the truth table in a certain way to see, oh, this is how I can use a NAND as an inverter, right? Or, oh, this is how I can use a NOR as an inverter. And then we, you know, looked at De Morgan's for, you know, how to get, you know, a NOR to be a NAND and so on. Okay, so, you know, again, that was, or those were examples of like understanding a truth table. You know, again, a lot of times when I, you know, talk to students and I go, you know, you really have to understand a truth table. They kind of look at me and they're like, well, what do you mean? Because it's just zeros and ones. I just look at it. But here's another example of understanding a truth table, okay? So if you look at this AND gate truth table and you just kind of, again, split it in half, and you only look at the top two rows. Okay. If you only look at the top two rows, do you see what it's telling us? It's telling us that if one input to an AND gate is a 0, the output is 0 regardless what the other input is, right? Because if A is 0, the output is 0, and it doesn't matter what B is, right? If B is 0, B is 1, it's still an output of 0, right? So if I have 1, 0 at the input of an AND gate, I don't have to know what the other inputs are. The output's going to be 0. Okay. Now, the bottom part of the truth table tells us something different. It tells us, well, if one input to an AND gate is a 1, the output's going to equal whatever the other input is. All right, so you see, again, that's an example of what I mean by understanding a truth table. Okay, and you're going to see that's going to help us analyze this MUX. Okay, all right, so let's just take the first row here. S is equal to 0. S1 is equal to 0. So both of the select bits is equal to 0. All right, now let's follow the lines here, the connections. So if you look here on this side, it goes through an inverter. So what's going to happen? It's going to get inverted, right? It's going to be knotted. So if I got a 0 on the input side of an inverter, it's going to make the other side a 1, right? So you see, I'm going to have a 1 on the input of this AND gate, and I'm also going to have a 1 at that input of that input, right? Now, also let me point out here before we go much further that you see where the lines cross? Where the lines cross, that's not a connection. Okay, in fact, sometimes you'll see this. Like you see right here, it made a little hump. Like sometimes they'll do that, but again, that's kind of old school. Like you'll see that like in older textbooks and older logic diagrams. The newer ones, they just, they'll just have them cross. See, if there was a connection, there would be a dot, right? So if there was a connection where you see a cross, there would be a dot. Okay, so like there's no connection, no connection, no connection, and so on. Okay. All right, now let's look at the other path here. The other path doesn't go through an inverter, right? So it's going to put a 0 here, and it's going to put a 0 here. So what's the output of this AND gate? 0. See, I don't care. I don't care what those other two inputs are because, as we just talked about, if you have a 0 at the input of an AND gate, the output's going to be 0 regardless what the other inputs are, right? Because it takes all the inputs to be a 1 to get a 1 out. So you see, I don't have to figure out what those other inputs are. I know this has to be a 0. Likewise, I know this has to be a 0. That makes sense? Okay, so now let's look at S1. Okay, well, you can see here, S1 is 0, so it's going to change it to a 1 here. And then we're going to have a 1 here. Oh, but we don't care. Just so we don't care about that. We already know that's a 0. So actually, yeah, so it puts a 1 here. Okay, and then let's look at this side. This side is a 0, and it puts a 0 here. So now I can say the output of this AND gate. Okay, so look, these three outputs of the AND gate are all 0, but this one up here, it has 2 of its 3 inputs equal to a 1, and then the other input is equal to our data, and this data can be either a 0 or a 1. See, all this data can be either a 0 or a 1. So what's going to be, this is our D0. So what's going to be at the output of that top AND gate? Yeah, whatever D0 is, right? Because if D0 is a 0, it'll make the output a 0. If D0 is a 1, it'll make the output a 1. So you see the output here is going to be D0. And now going into the OR gate, you have a 0, 0, 0, and D0. So when D0 is a 0, what's the output gonna be? 0. When D0 is a 1, it's gonna be a 1. So the output is D0, right? Because whatever D0 is determines what the output of the OR gate is. So you see, when both select bits are 0, you get data D0 out. See, that just proves what we talked about earlier, right? That if you make the select bits 0, D0 gets connected to the output. And, we could do more rows. Does anyone want to see another row, or can you, you can take my word for it, or you can just do the rows yourself. But if you take 0, 1 and put them in for our bits here, our select bits, you're going to see the output equals D1. That only this AND gate's going to matter. And then for 1, 0 at the select, we'll get D2. And if this AND gate's the only one that's going to matter, and then we select bits of a 3, this bottom AND gate's going to be the one that only matters. Okay. So, this is the nitty gritty, but the big picture and the reason why I wanted to spend some time going through an example like this is that, these devices that we're going to start talking about today, it's a MUX today, it's a decoder next week, it's going to be a register a week after that. You got to remember, they all come down to gates. Okay. All right, move camera. So any questions as I move the camera? No questions. Let's see.
How would you take
What's that?
I was gonna say, how would you take them and figure out the logic? I think
Well, you would do what we have been doing, where you would start with a truth table like this, and you would write, if you were going to do it manually, you would write out equations like we've done and put it into K-maps and so on. Yeah. Again, we don't do that anymore in these programs. Yeah, and then something like a MUX is, what we refer to as a standard logic device. So, you would never design a MUX. You would just look for the one that fits whatever your particular application is. And then, what most practicing engineering is that you'll have some problem that you're trying to solve, and what's available isn't quite what you need. So you take what's available and then modify it, make it fit or interface it. That's what most practicing engineers do. Most practicing engineers don't start from scratch. Unless you're R&D, like research development, something like that. But usually that's more experienced. Although there have been students coming out of Cal Poly that have gone to work for research labs. So I don't want to say everybody, but yeah, because I know Amazon's research lab has hired our students.
When you put the 0 1s next to the inputs, and then you put a sync, so the 0 1, does that represent the number of bits for each D0, D1, D2, D3?
No.
Are they all going to be?
You're talking about when I write at 0 equals 0. And
Yeah.
Yeah, remember, it's a good question. You always got to remember the 0s and 1s are just shorthand for voltage. So this 0 would be connecting that input to ground in a circuit.
Okay.
And a 1 is a plus amount of voltage. So that would be, if I made this bit of 1, that's like connecting it to plus 5 volts.
Okay, so it doesn't have anything to do with the bit representation.
Well, remember, if there's more than one bit, there'll be a slash with a number.
Yeah. Okay. That's
So yeah. So this would all be just single bit.
Okay.
Yeah. But the concept's the same no matter how many bits you have.
Yeah.
Okay, so the next thing to talk about is when you have a MUX, how we typically represent a timing diagram. Okay, so this is important for a couple of reasons. One reason is to do the activity, but also when you're dealing with any sort of like real situation, you know, like hardware, like for your lab 3, or when you build that microprocessor in CP233, like you've been doing, you got to look at a timing diagram to see if your circuitry is working. Okay, so here's an example of a timing diagram for a MUX. So what kind of MUX is this? A what to what? 4 to 1. Yeah, 4 to 1. Again, this just means 4 inputs, 1 output. It's always 1 output. So the only thing that's different is the number of inputs. So you can see we've got 4 inputs, and each of the inputs is 8 bits, and the output is 8 bits. How many bits would we need for the select since there's 4 inputs? 2. And again, it doesn't matter. If these were 16-bit inputs and 16-bit outputs, it would still be 2 select bits because the number of select bits depends on the number of inputs. Okay, the number of bits on each input has nothing to do with the number of bits for the select. That's the most common error people make. All right, so what we're going to do here is we're going to come up with what the output is based on these values for select, and then the data. You know, this is data. Now, you know, it's labeled AA, but it's still data. So we've got these 4 data inputs, and we're going to determine what data gets to the output based on these select values. Now, one thing you haven't seen before is this 0x. You know, there's 0x3, 0x24, and so on. 0x means that what follows is in hex. All right, so 0x is another way. You know how we were doing like A3 base 16 by putting a subscript 16. Well, instead of doing that, you could do this 0x A3. All right, it's the same thing. Okay, so you see all these values are in hex. So like any timing diagram, you start on the left, right? That's our t equals 0, and you just work your way to the right, and you have to reevaluate your output whenever there's a change in input. So you can see here that we have a select of 3 until this time. That's when the select changes. Okay, but during this time when the select is 3, what data are we going to get at the output F? Is it going to be DE?
7, 9.
How'd you get 7, 9?
Oh, okay.
Yeah, see, I did this on purpose. Over here, I made the top input 0 and the bottom one a higher number. Or right here, I made it 0, 1, 2, 3. Here I did 3, 2, well, this was out of Dr. Muley's book. It's done 3, 2, 1, 0. That's just to show that when you have a MUX symbol like this, the numbers for the inputs can be either, you know, top to bottom or bottom to top. Okay, it can be either way. So what's the data going to be now that you realize it goes 3, 2, 1, 0 instead of 0, 1, 2, 3? or. Right, it's going to be whatever's on the AA input. Okay, so it's going to be 24 hex. Okay, and then you can see the select changes here. It goes from a 3 to a 1. Okay, so you see during this time, when the select is a 1, what data are we going to have?
It also changes. Well,
So
Yeah.
it's gonna be pretty much 8.
When it's a 1? Well,
When it's a 1, it's gonna be 0x83.
That's gonna be 0x22 and 0x.
okay, so when this select input is a 1, which data input gets connected to the output?
You see,
Yeah, CC. So now you look at CC, right? So you see during this time here, it's hex 22, and then it actually changes to A3 a little later on. Okay, so, you know, it will be, during this time, it will be hex 22, and then it changes to the A3. Okay, so everybody see that? Right, it changes at the output because the data on CC, which is being selected, also changes at that time, right? Everybody agree? Do you want to do one more? Yeah, let's do one more. Okay, so now it changes the select. Okay, it changes from a 1 to a 0.
It's gonna be, X of 2,9 and then X of FF.
Right, yeah, because when the select is 0, now the data on input 0 gets connected to the output. So you look at DD, and during this time, it's a 2A hex. So 2A, and then here it's going to change to FF. Does it make sense to everybody? This is another review question. Does it make sense to everybody that since the inputs are 8 bits and the output is 8 bits, that when the data is written in hex, there's 2 characters? See how it's B1, 2, 2, 2A, 8, 0. Does that make sense? It should make sense to you that since each input is 8 bits and the output is 8 bits, that all of these inputs and output data in hex is being represented by 2 characters. Why should that make sense to you?
Because X bit is for binary bit.
I remember this was back to day 1, right? When we were doing number bases, that if you have a hex number and you want to go directly from that hex number to binary, each hex character is a 4-bit group, right? So 3A in binary, I would just write A in binary, which is 10, and I would write 3 in binary. Right? Remember that? Okay. Can't forget stuff that we've already covered, right? It all builds on each other. Okay, so does anyone want me to keep going? Because it just gets repetitive. I mean, it's the same process, but if you understood what we did here, you should be able to do the activity. The activity is doing timing diagrams like this. Okay. Want to proceed? Everybody's okay for me to keep going? All right, so now, okay, so now we're going to get to something new in Verilog. Up to this point, when you've modeled any sort of hardware at Verilog, you've used Boolean expressions, right? You did that in lab 1, you did it for the lockbox. Well, you did it in lab 0, then you did it for the lockbox in lab 1. And then, the most recent lab 2, the RCA, right? When you did the half adder and full adder, you're using Boolean expressions. Well, from here on out, we're not using Boolean expressions anymore. Okay, we're going to start letting Vivado do the work. Okay, because in Vivado, just like in high-level languages, you can use if statements and case statements. Okay. Now, again, I want to stress that even though the if statements and the case statements look very similar or exactly like what you've seen before in other high-level languages, Vivado, what you write are not instructions to a microprocessor like they are in a high-level language. Okay, you always got to keep in your mind that code, even though it looks like a high-level language, it's code that represents hardware. Okay. See, the big difference between the two is that the code that represents hardware can have parallel functionality, just like a circuit does, where instructions to a microprocessor are, do this, do that, do this, do that. Okay. So you see, with Verilog, you're modeling hardware where things can happen at the same time, because that's what you need, because that's how hardware works. Okay. All right. So what I'm going to show you next is how to do an if statement in Verilog, system Verilog, because you're going to do an if statement for the MUX that's part of lab 3. But as an example of an if statement, I'm going to do an if statement for a device called a comparator. Now, again, I want to repeat what I said earlier. The comparator is not part of lab 3. It's not part of any lab this quarter. Now, you may, depending on what kind of team project you do at the end of the quarter, you may want a comparator. And you should know how a comparator works because it's a common, digital device. But the purpose of me showing you the comparator now is as an example, okay, of an if statement. So let me get my notes out here so I limit my syntax errors. I can't 100% guarantee that there's no syntax errors in here, but the main reason I want to, or I'm showing you this is so at least you'll get the format. Okay. All right. So first thing is that just like any module, you got to give it a name, and then you're going to define your inputs and outputs just like you've been doing, right? So you have like, input, and then in brackets, depending on how many bits here. Like say you had 8 bits, you would put 7 here, right? So you take that number -1. So I'm just kind of doing it in general terms here. And then the least significant bit is always 0. Okay, so you would actually put a number here. I'm just doing it in very general terms. Right? I'm not confusing anybody. No one's going to write number sign -1. Okay. And then, whatever you call it, okay. Now, you would do this just like you've been doing, but there is one difference that has to do with the output that I'm going to come back to in just a second. Okay, so I'm going to write output, and over here, I'm going to leave a space. And then over here, I'm going to put the same thing. Well, here our outputs are just single bit, so we don't put the bracket, right? Because see our outputs GT, LT, and EQ, they're all single bit. So I put GT. And like I said, something's going to go here, but I'm going to come back to it in just a moment. So, you would put your inputs and outputs just like you've been doing. They're commas, right? Thank you. See, I told you. These would be commas. And then eventually you get down to parentheses, semicolon, right? Okay, thank you. Okay, so, right, so mostly it's the same as what you've been doing, except we're going to add something here in just a little bit. Okay, but here's the next thing that you haven't seen before, and that's when you have an if statement, it has to go within what's called an always comb block. Okay, so the next thing you would have here is you'd have always underscore COMB. And you need a begin. So this COMB is short for combination. And we haven't mentioned this before. This is another term. But combinational, that's logic circuitry that does not have memory. Okay, so combinational logic, there's no memory. In about, let's see, I think it's the class before the midterm. That's when we'll first discuss, what memory is. Okay, which is under what's called sequential circuits, sequential logic circuits. All right, so you get this always comb, then begin. Then the next thing that we would have is that, we would start our if statement. So this is a comparator. So you can probably guess what GT, LT, and EQ stand for, since it's a comparator. It's going to take these two inputs and compare them. So what do you think GT stands for? Yeah, greater than, less than, or equal to. Okay, so now comes the if statement. If A is greater than B, we need another begin. I'll explain this coming up. Okay, but if we have A greater than B, we're going to make output GT equal to 1, output LT equal to 0, and output EQ equal to 0. Okay, and then we would put an N. Okay, so this begin is for the always comb. This begin is for this part of the if statement.
Period. But do we not need to say assign for an if statement?
No,
Okay.
yeah, that's one of the things that's different. Yeah, that within this always home, you, in fact, if you do put in a sign, you'll get an error. Yeah. Yeah, you cannot, I'm glad you asked that question. Because yeah, that's a common thing. You cannot have assign statements within an always block. See, this is an always comb. There's also just an always block that we'll also talk about in a little bit. And there's also what's called an always FF, which has to do with sequential circuits that we'll get to in a few weeks. But any kind of always block, you cannot have an assign statement. Okay, assign statements are only outside always blocks. And also you can have assign statements in your structural model. In fact, that's usually where you put them. Okay, usually, you know, just like you saw in the activity last class, you know, where you had the code making connections, but then there'd be an assign, like if you had a gate or something, that's typically how it's done. So. Okay, so you see this part of the if statement where you see the begin end here, that's necessary when you have multiple outputs. See, we have multiple outputs here. If we just had a single output, you don't need this begin, you don't need this end. You could just put if and then just write what that single output is. You only need the begin end for the if part of this if there's multiple outputs. Okay, now here's where we're going to go back to the outputs here. In fact, I only put one output, but let's put all of them. They're all single bits, so I'd have GT, LT, and EQ. And then I'd have a common. Well, when you have an output within an always block like this always home, you have to put in between output and the name of the output, you have to put logic. Okay. You only need to do this when you have outputs within an always home, like an if statement like this. So, you know, if you have something like we had before, like in lab 2, lab 1, lab 0, where we didn't have any always block, then you don't do this, because if you do it when you don't need it, it will create a problem. Okay. All right. But now with if statements, you can have 0 else ifs, or you can have as many else ifs if you want. Okay, so you can have just an if and an else, or you can have an if, else if, else if, else if, else, you know. So the number of else ifs are, you know, whatever you need. Could be 0, 1, 2, 3. Here we need an else if, but we got 3 possibilities. So the next thing we would put here is else if. I believe it's all. I'm not sure. You might get a syntax error on this. I'm not sure if you put a space or not. I don't think you have to, because white space doesn't matter. If when you do this, you get a red line, it probably means it needs a space, but I don't think it does. But anyway, else if A less than B, begin. This would be GT equal to 0, LT equal to 1, EQ equal to 0. And then you would end it. Okay. And then we would need an else. So we have else A equal, or actually we don't need A equal, because it would have to be that, right? If it's not less than or greater than. So we just have else and then begin. And then we would have GT equal to 0, LT equal to 0, EQ equal to semicolon. And then we have to end this beginning. So you always have to make sure the begin and the ends match up, right? Like this begin needs an end, this begin needs an end, this begin needs an end, and then this begin needs an end, right? The end that always comes. So you need another end here. You need another end, and then you'd have end module.
It's kind of like curly brackets that you would see in high level code.
Right. Yeah, exactly, yes.
Okay.
Yeah, this, have you had C programming?
I've done C++ a lot.
Okay, yeah, because, System Verilog, it's based on C.
Okay.
Yeah. You know, also Arduino is based on C. So yeah, if you're EE or CPE, it's really nice to know C, C++. So there's a lot of other languages that are based on this thing, so. All right, so do you have any questions? This is the basic format. Again, I might have made some syntax errors, you know, if I did, I apologize, but I have a hard time remembering syntax, but yeah, usually syntax errors are easy to fix. It's the logic errors that can be nasty. Okay, well, let me show you another way to do this. Another way that you might find a little easier. Okay, this is kind of like the straightforward way, but there's another way that's not that fancy, but I like this way. The other way is the basic difference is that you initialize your outputs to some value, usually 0. And if you initialize your output values to 0 to begin with, then you don't have to list all the outputs in your if statement. You can just list the one that changes. And by doing that, then you don't have to keep doing these begin ends, because like I said, you only need these begin ends within the if when you have multiple outputs. If you have a single output, you don't need to put the begin end. Okay, so if you want to initialize output values, you just do this. You go initial, and then begin, and then you would just list your outputs and set their values. So I'm just going to set them all to 0. In this. Okay, now you do your always. Please home. And now, when you do the if statement, right? If A greater than B, you would just put the output that changes. So this would be GT equal 1 to semi. And then,
Would you need a begin? Oh, you said no, you put, right?
yeah, that's the key thing. If you initialize your values first, now you only have, within the if, now you only have to put the output that changes. And because it's a single output, you don't need this begin end like you did here. That's why some people like this. You know, it kind of saves you some, you know, especially if you got a lot of output. So, and then you would just keep going, you know, then you just have else if. Yeah, I'm pretty sure else if is all one. There's no space. Because in my note, I kind of had a space here, but here I don't. Pretty sure there's. But then you go A less than B. And LT equal to 1. Semicolon. You know, else. EQ. And then you would end this begin. And then end margin.
Do you need the else if? Because if A is greater than B, the only. Oh,
Well, they could be equal though.
right.
Yeah.
Yes, in asking my question, I can answer it.
Yeah, that's fine. Yeah, that's fine. Yeah, so anyway, like I said, you know, this is kind of like the standard way. This is, you know, a little bit tricky, but it's just initializing the values first, that's all. And it saves, I don't know, it looks a little shorter to me, but it saves you all these begin ends. Okay, so any questions up to this point? Now, if you understood this, the if statement that you have to do for the mux is much simpler than this. Okay, because turn the camera. All right, because here's the mux that we want you to design for lab 3. It has 2 inputs
Okay. Forgot to do this, but the output's also 4 bits, so there should be a /4.
So it's got two inputs where each input is 4 bits, and like always, right, it's one output, because all muxes have one output, so you know, this is a 2-to-1 mux. So since we only have two inputs to choose from, how many bits is the select? Yeah, it's just a single bit, right? When it's a 0, A is gonna be at the output. When it's a 1, the B input's gonna be at the output. So you just have to model this 2-to-1 mux with a single if statement, and it's easier than this. Are you gonna need an else if for this? No, it's just if else, right?
And then we're only gonna have like 2 test cases.
Yes, I was gonna ask that later. Where is that? Yes. Why 2 test cases?
Because that's the amount of inputs we select.
Yeah, right. If I do a test case where this is 0 and I do a test case where this is 1, it works as long as I'm getting the expected output, right? When this is 0, I should get A. When this is 1, I should get B. You just gotta do 2 test cases. Right? So what you can do, after you do the activity day today, you can get started on lab 3, but like I said, you can't finish it until we talk about decoders on Tuesday. But what you can do today after the activity is, create a separate project for lab 3. Again, I hope you're doing that for all the labs. And then go ahead, design your mux with an if statement, right? That's gonna be your design source. Go ahead, do the sim file. It's only gonna have 2 test cases. Simulate your mux. If it works, great. And again, if you get your mux working before Tuesday of next week, then you'll be right up to speed with what you can do. And then the other thing you could do is lab 3 also uses the RCA from lab 2. So you can just bring over your design source for your RCA into lab 3. And provided that it's simmed okay in lab 2, I mean, assuming your lab 2 is good, you don't have to resim your RCA. You already know it's good.
We need the half hour.
Yes, yeah, because the RCA is made out of the half adder and full adder. Yeah, when you bring over your RCA, you got to bring over your half adder and full adder. Yeah, because remember the RCA, that structural model, it basically references those, right? Yeah, so you need them. Yeah, I'm glad you actually said that out loud. Yeah, that's something that people often forget. Okay, so that's today's class. Now, just a little preview of Tuesday of next week. Tuesday, we're going to talk about decoders. We're going to concentrate on a decoder called a 7-segment display decoder. So lab 3, instead of your output being shown with LEDs, it's going to be actually shown on one of the 7-segment displays that's on your basis board. So on Tuesday, after we talk about decoders, you'll design a 7-segment decoder. You'll sim it. Then you're going to have to connect an RCA to a mux and to a decoder. The actual, structural diagram is on Canvas. Start with lab 3 instructions. So you'll need, like a structural file, just like you had the RCA file. And what this circuit will do is that it will add A and B like you did in lab 2, but it will display the result on a 7-segment display as a hex character. So it's like an converting hex circuit, if you will. Yeah. So, like maybe you'll call your structural model file like add convert mux or something, like add _ conv _ X or something, to be descriptive. I mean, you can probably think of something better than that, but it's probably what I did. Okay, so unless there's questions, that was the lecture today. So yeah, work on the activity. Everybody should have a handout. If you don't, let me know. I can get you one. The activity is just filling out